we have discussed the design of ALU with respect to addition, subtraction, comparison and logical operations. We have also discussed other operations like shift. We will continue on this and take a slightly more complex operation, namely multiplication. So, we will see how a multiplier can be designed both for signed case and unsigned case, and in the next lecture we will move over to another operation which is complex, that is division. So, in the plan of lectures we have reached this point, going to talk of multiplier design. So, we will begin with the very simple design, shift and add multiplication. We will see how you could build the circuit following this shift and add approach. We will see multiple ways which differ in terms of cost of hardware, okay, or simplicity of hardware. Then we will talk about signed multiplication, where you can either do unsigned multiplication, then take care of the sign separately, or do directly signed multiplication. We will see what are the essential differences in the circuits which are required for signed and unsigned multiplication. So, let us begin with multiplication as we do with paper and pencil. A simple multiplication method as we are all used to. Only thing is that we do in decimal system, and the same thing translated to binary in fact is even simpler, as you would notice. So, suppose you have a 3-bit number A which has to be multiplied by another 3-bit number B. So, as usual we will multiply A by each bit of B with suitable weightage and simply add them. So, multiply by the LSB of B, we get 0 1 1, multiply A with middle bit of B, you get all zeros, multiply with the leftmost bit of B, you get 0 1 1. So, basically individual multiplication is multiplication with either 0 or 1, which is very straightforward. Multiplication with 0 results in 0, and multiplication with 1 results in the same multiplicand itself. Okay. And these partial products, okay, each line represents a partial product, they have to be weighted appropriately, and the weightage here is power of 2, which means shifting it appropriately towards left, and simply add all these. So, that is a simple way which we will try to capture in hardware, and the way hardware will work is that you will start with a 0 value in some register. Okay. You can add first partial product to that, you get this, add second partial product, in this case of course there is no change, add the next partial product and you get the final result. Okay. So, basically you are carrying out addition of initial 0 value and this partial product to get this, then next one is added, and then the next one is added. So, as you can see, the whole thing breaks up into multiplication by 0 and 1, shifting by successively 1, 2, 3, 4, so many positions, and adding all these up. So, we have already seen each one of these individually. We know how to add, we know how to shift, and of course, all we need is to multiply with 0 1, which means performing essentially an AND operation. Okay. AND operation actually is equivalent to multiplication by 1 bit. So, we can express this as a summation where A is multiplied by bits of B, that is B I, with a weightage of 2 raised to power I, and we sum it over all values of I going from 0 to n minus 1. So, this is the unsigned multiplication, and the circuit for doing this can be easily built. First thing we are trying to do is multiplication with a 0 or 1. Okay. So, it is effectively A is multiplied by one of the bits of B. So, here I am illustrating with a 4-bit situation. So, this AND gate actually represents an array of AND gates, where each bit of A is ANDed with B 0. Okay. So, in abstract term I am showing a single AND gate, which is where we are taking a vector of bits A and a single bit B, and output is a vector. Okay. So, strictly speaking I should have marked the size of the vector going into or out of it. Okay. So, each of these AND gates is effectively an array of 4 AND gates. So, what I am getting here at these points is the partial product. A is multiplied by 1 bit of B, and then I require shifters. Okay. So, each of these shifter is doing shifting by a fixed amount. All right. So, it is only a there is no active logic here, it is only appropriately wiring it, right. These shifters do not have to select between shift and no shift, it is a fixed shift which each is doing. So, it is simply a matter of wiring it appropriately, so that effectively shift takes place. And the next stage is addition. So, starting with a 0 here, we add first partial product, then second partial product, third and fourth, and finally, we have the product of A and B. So, when I say that these shifters are simply wiring, it means that these 4 bits are connected at appropriate points at the input of adder. Okay. You connect directly or shift by 1 position or shift by 2 position or 3 position, as the case is. All right. So, this is one very simple way of capturing this idea of summing the partial products to get an unsigned multiplication. Is there any question about this? Okay. Now, this requires n adder. If you have n by n multiplication to be carried out, this will require n adder, each is adding one partial product. We can simplify the circuit by using same adder several times. Okay. So, we can capture this in the form of an iterative algorithm. So, I am keeping a count I, a sum s is initialized to 0, and then I do something repeatedly. So, there is a loop where A into B I multiplied by 2 raised by I is accumulated, I is updated, and I repeat it for all values of I. Okay. So, what I am trying to indicate here is that there is an initialization step, which is step 1, and step 2, which is repeated n times. So, step 2 is both these assignments. So, actually what I imply is that both these are done together in the same clock cycle. So, for n bit multiplication, this would be done, this loop will be done in n clock cycles, although I have written as 2 separate assignments, but my intention is to do these 2 in hardware in a single cycle. Now, there could be some improvements made in this. Instead of adding A multiplied by 2 raised by I, what I could do is I could actually keep on shifting A itself, okay, keep on modifying A. So, every cycle A will get doubled, all right, and then I need to add A only. So, let us see the algorithm with this modification. So, instead of saying S accumulates A into B I into 2 raised by I, this I am putting as a condition that if B I is 1, then I do this accumulation, otherwise I do not do this addition. Okay. And in any case, whether S I is whether B I is 1 or 0, A is doubled every time. So, I could say A is doubled or shifted left, it same thing. And all these 3 activities are done in a single step. Okay. As I add A to S, I prepare the next value for A for the next cycle in the same step. Okay. So, this whole thing is one clock cycle as far as hardware is concerned. Updating I, doubling of A, and conditionally accumulating of A. All right. So, basically shifting of A here is taking care of this multiplication by 2 raised to power I. So, since I am doing it sequentially, I can keep on incrementally shifting it every time. The next modification here is that instead of looking at different bits of B in successive iterations, I can keep on shifting B in a register, so that I always look at B is 0. That will also simplify the hardware to some extent. Rather than trying to look at different bits in different cycle, I look at same bit, but move the bits in such a manner that I need to focus at the same point always. So, here I am checking B 0 always, but to compensate for that, I am making B as B by 2, or which means B is right shifted every time to get the same effect. Okay. So, now let us take this and look at its hardware equivalent. So, it is the same algorithm. What I require is essentially a mechanism to add A to S. Okay. So, here is an adder, A is one input, S is another input. I am not showing how I am making S as 0 initially. So, that detail is omitted, but this will take care of performing the step of S gets S plus A. Okay. And to take care of this, A will be shifted left after A supplies while A forms an input to this adder, A will also make itself ready for the next cycle. So, at the edge of the clock, S plus A is stored into this, and 2 A is stored into A. Okay. So, these two events will happen concurrently with edge of the clock. Now, one thing you should notice here is that this adder has to add 2 n bit numbers. When you are talking of 2 n bit, A and B both are n bits, but as partial products are effectively shifted to left, we need adder of double the size. Okay. First addition would be done at one extreme position, and the last addition would be done at the other extreme position. So, adder has to be wide enough, essentially double the width to accumulate all these values, and this register which will hold A also is of double the length. So, the operand initially is placed in the right half. In the right half, the value is placed, and it keeps on shifting to the left, and by the end it has reached the other end. Okay. So, this is the key part of the circuit, and to control this, we require another register holding B, which will experience a right shift. So, in every iteration we shift B right, so that we are always looking at B 0 position, which is the LSB of this. So, this has to work in conjunction with a control, which firstly takes care of this iteration count. The process has to be repeated 32 times. So, it does the counting, and it also times the operation of all other units. Okay. So, I am showing these red signals which are control signals. This is working under control of B 0. So, with depending upon the value of B 0, it will actually instruct addition to be done, or either this circuit will pass on the value of A here, sorry, A plus S, or just S itself. Okay. So, there is some logic here which either performs S plus A or S plus 0. Okay. So, that control is here, and this is this and this are basically to time the operations of these 3 registers when they shift and when they store the new value. Okay. So, this is the essence of the circuit. There are some details which are omitted here, but what I would like you to notice here is how we are going from step to step and what is each crucial step here. Okay. So, each step basically involves these things: checking B naught, performing addition conditionally, left shift of A and right shift of B, and update of a counter. So, that counter I am not showing explicitly, it is part of the control. Okay. Now, let us do something so that requirement of 2 n bit addition can be cut down. So, we can manage with n bit addition, then something here will be simplified, and the idea of this comes from, let me get back to this diagram, this one. So, you would notice that at any time one of the values which you are adding is only n bit, and it is only when you look at the whole thing it is 2 n bit wide, but if you look at each addition you are adding one n bit value in some position. So, if you focus on that, you need to have only n bit adder. Okay. There is nothing changing on right of it, there is nothing changing on the left of it. So, if you arrange your information such that you are taking care of those n bits where the new value is positioned, you can work with n bit adder. Okay. So, here is the modified circuit, where what we are trying to do basically is that we are adding A to the left half of S. Okay. SH is denoting the high end of S or the upper half of S. So, A is always added in that position, and we are making sure that the two are correctly aligned. So, what we will do is we will be shifting S to right every time. So, initially S contains 0, you add that to the left half of S, then it is shifted. Okay. S is shifted to right, then you add A to again the same position. So, it is the partial product which you have accumulated that keeps on shifting right, instead of shifting A to left in every cycle. We are shifting the partial product obtained so far to right, which actually maintains the same relative position and achieves the same effect. And the consequence of that is that adder needs to be only an n bit adder. So, A is now n bit register, A does not shift at all. The value A gets added to left half of S, and after addition you can shift S to right. So, I have introduced another step here, that after this addition S becomes S by 2. So, which means you are shifting it right, and rest of it is same. Okay. B has been shifting right, the counter increments. Okay. So, the crucial change is here that addition is only to the left half of S and S shifts right. Although I have introduced this as another step, but it is actually possible in principle to do all this in a single clock. Okay. I will not go into details, you can just take my word for it for the moment, but it is possible that the final value which has to be there in S as a result of summation and shifting, you can actually look at that and place that in S directly in a single step. So, that is not very difficult, but just for conceptual clarity, we assume that first A is added, okay, and then shift is done. So there is one more subtle point here, is that when you are shifting S right, there is a carry which will come out of this, which might come out of this, that has to enter. So it is not a pure simple right shift with 0 getting stuffed into the vacant position. It is this carry which you do not want to lose. It is an intermediate carry which has to be accommodated here. So apart from that subtle consideration, it is very straightforward. What we have achieved is, we have reduced the size of this register by a factor of 2, we have reduced the size of adder by a factor of 2. Okay. And having done this, there is another interesting observation which can be made, is that we have now two registers S and B which are shifting right. Okay. So initially S has all zeros, and as you perform addition and shift right, you keep the bits keep trickling into the right half of S. Okay. Initially everything is 0. So as partial products get added, one by one bits keep on entering the right half of S. Okay. At the same time, B this register is filled with value B, and as you shift right, it keeps on making spaces on the left side. So this observation leads to the possibility of combining S and B in the same register. Okay. So what I am saying is that initially right half of S is vacant, and it is getting filled up gradually bit by bit from the middle. Okay. Whereas B initially is full and getting vacated bit by bit on the left side. So the two actually match. So the two together never require more than 2n bits. So what we can do is, we can actually initialize S with 0 in the left half and B in the right half. Okay. And then look at the rightmost bit of S instead of rightmost bit of B, and rest remains the same. So the initialization of S is different. We have 0 and B put together forming 2 n bit word, which is put in S, and okay, yeah, here shifting of B is avoided. There is no B register now. So S becomes S by 2, which is a right shift, and rest of it remains same. So this is the final circuit which I will leave at. It requires one 2n bit register, one 1 bit register, and a single n bit adder. Okay. Any questions about this? In MIPS we have a multiply instruction, which actually takes 2 operands in 2 registers, and it produces a 2n bit result, okay, which are kept in 2 special registers. One is called high, one is called low, HI and LO. So there are special instructions which can be used to move data between these registers and one of those 32 general purpose registers. So but the output of multiplication goes to those specific registers, high and low. Actually there is also a pseudo instruction for multiplication, which takes 3 registers. So 2 for operand, 1 for result, and that actually expects small numbers, so that the product is within within 32 bits, and it ignores HI. Only LO is looked at and automatically brought into one of the registers. Okay, now let us move towards sign multiplication. Okay. So there are 2 approaches to this. One is, we handle sign and magnitude separately. That means, if there are 2 sign numbers, we find their magnitudes, multiply them, get magnitude of the product, and determine the sign. So sign, you know, is if the 2 numbers are opposite sign, then the sign is negative. If they are of same sign is positive. And once we know the sign of the product, you can put it back in the appropriate form, 2's complement or whatever approach you have. The second approach is to directly multiply sign integers. Okay. So, unlike addition and subtraction, where this 2's complement representation made it possible to look at sign and unsigned addition subtraction identically except for overflow reduction, but the addition subtraction process was oblivious of whether there is a sign or not. Okay. For multiplication, that does not exist. Okay. So, we have to devise a method which can directly multiply signed numbers, and what that requires is a common expression representing the values of positive as well as negative integers. So, we expressed the number in terms of its bits in this form. Okay. Here you see basically we have expressed b as a summation of b I into 2 I for different values of I. We need to find something which handles positive as well as negative numbers. Okay. Again, representation we will use 2's complement, and this representation is shown here. So, you would notice that there is similar kind of summation, but it goes to bit n minus 2 only. The last bit, which is a sign bit, is handled separately. So, all that we have done is put a negative sign with this, right. So, again the weightage is 2 raised to power n minus 1 here, but the only difference is that this comes with a negative signs. So, why is it so? We can see it here. So let us look at two cases. What happens when the number is non-negative, okay, and what happens when the number is negative. So, if b is non-negative, we could have expressed this in this form, okay, that is the usual thing for unsigned numbers. But since b n minus 1 is 0, because the number is non-negative, the sign bit is 0. Therefore, if we pull out the last term and put a different sign, it does not matter, this term is 0 in any case. Okay. With b n minus 1 as 0, whether you put plus or minus, it does not matter, because this part is 0. So, a positive, a non-negative integer b can be expressed in this form. All right. So, this part is this case is very straightforward. The other case is that of negative numbers, which needs a little bit of analysis. So, when b is negative, its value is basically minus magnitude of b. Okay. So, this represents this is the magnitude of b prefixed with minus sign is what b is all about. Okay. Now, let us see what the magnitude of b would be. So, since it is a negative number, we can express we can find the magnitude by knowing that it is a 2's complement representation. So, 2's complement representation means 2 raised to power n minus weighted sum of the bits. Okay. So, this is the interpretation of that number had it been an unsigned integer. So, to find its equivalent magnitude, treating this as a negative number, we take that value and subtract it out of 2 raised to power n. So, this is by definition of 2's complement representation, that you subtract this from 2 raised to power n. So, now this summation can be broken up. We take n minus 2 terms, keep them inside the summation and bring out the one which corresponds to the sign bit. Okay. Now, b n minus 1 is 1 in this case, right. So, this thing is nothing but 2 raised to power n minus 2 raised to power n minus 1. Okay. Since 2 raised to power n is nothing but 2 times 2 raised to power n minus 1, this difference will correspond to let me write it here. This whole thing outside the summation is equivalent to 2 raised to power n minus 1. I am sorry, 1 in the subscript. Okay, let me. So this whole thing is equivalent to this, which I have rewritten, bringing b n minus 1 back, because that is, this is equal to 1. So, I can write this multiplied by b n minus 1, which is 1, to get in this form. So this thing substituted here, so I get minus b n minus 1 2 raised by n minus 1, and that becomes positive. So, I get this. So I have shown that both positive and negative numbers, when they are expressed in 2's complement form, can be captured by a single expression. Okay. So, now we have an expression which ignores whether it is a positive or negative number, and we can multiply the two together. So, direct sign multiplication is basically a multiplied by this expression, but I work on this little bit more on this expression to get to a convenient form. So, first of all, let me expand this. What I get is this first term with negative sign, all other terms with positive sign. Okay. Now, all other terms are broken into two parts. So, for example, this b n minus 2 into 2 raised by n minus 2 is written as this, okay, sum of these two terms, whereas effectively I have put a factor which is double of that. Okay. If you take b n minus 1, you can actually verify it by working reverse. Take b n minus 2 common out of these, you get 2 raised by n minus 1 minus 2 raised by n minus 2. Okay. This is this actually is twice this. Okay. So, what you will get is this. So, if I break each of these terms like this, I can then combine the term with same power of 2. So, for example, here these two have same multiplying factor 2 raised by n minus 1. What I get is b n minus 2 minus n minus 1. Similarly, this term will combine with the next term involving b n minus 3 and so on. So, what I get is this summation of b I minus 1 minus b I weighted with the 2 raised by I and summed over, I goes from I think this should have been 0. Yeah. So, this is 0. But to facilitate writing in this particular manner, I have introduced a dummy b minus 1. Okay. This goes up to b minus 2, but otherwise this term will remain unpaired. To combine it with another term, I have introduced a pseudo term which is actually 0 by definition. So, assuming that b minus 1 is 0 by definition, I can introduce a last term here, so that every term gets paired, and then this formula can be written uniformly, right. So, given this representation of b, you can write a multiplied by b as this summation. Okay. It is just that in this I bring in a within the summation. So, now what does it require? It requires partial products to be formed according to this. Okay. Instead of multiplying a with b I, which is 0 1, I am multiplying a with this term, and this can have what are the values it can have? It can have a 0 value, plus 1 or minus 1. Okay. So, still things are not too difficult. Minus 1 would mean that I take actually minus a. So, this partial product would be a 0 or minus a, and adding minus a means basically subtracting a. right. So, I have something which is very similar to what we had done. There are just a few differences which I will enumerate. Incidentally, this is called Booth's algorithm. So, let us compare unsigned multiplication and signed multiplication here. In unsigned multiplication, what we saw earlier, we look at bi, which can be either 0 or 1, and accordingly we either perform no addition or perform addition of a. Whereas, signed multiplication, we look at 2 bits together, okay, bi and bi minus 1. Actually, we are looking at this minus that. So, which can have a value 0, 1 or minus 1. So, when both are 0, we have no addition, nothing to be done, no addition, no subtraction. When this is 0 and this is 1, since we are doing bi minus 1 minus bi, we need to do addition of a. When this is 1 and this is 0, we subtract a, and when both are 1, again we require no addition. So, with this small change introduced, all the circuits which we had could be made to work for signed multiplication. Okay. The only thing we need to remember is that what we had shown as adder needs to be capable of performing addition and subtraction, okay. And there has to be little logic which looks at the pattern of bi and bm. It looks at 2 bits and decides, instructs that circuit to perform either no addition or subtraction. Well, this algorithm which I mentioned as Booth's algorithm was originally devised not for signed multiplication. Its motivation originally was something different, and which was as follows: that if you have, let us look at the multiplier b. If you have a row of ones, okay, as per the logic, we are doing something when there is a change from 0 to 1 or 1 to 0. Let me go back to this one. See, when both are 0 or both are 1, there is nothing required. When you are going from 1 to 0, there is an addition. When you are going from 0 to 1, there is a subtraction. Okay. So, let us say this is part of the word comprising b, and you are scanning the bits from LSB to MSB. So, when you have a run of zeros, there is nothing required. When you have a change from 0 to 1, then you perform subtraction, and when you have a change from 1 to 0, you perform addition. All right. So, another way of understanding this is like this, that you can write a number like this as 1 0 0 and subtract a 1 from this position. Okay. So, actually it is this one which corresponds to one subtraction, and this corresponds to an addition. All right. So, when this algorithm was devised by Booth, the attempt was made to minimize the number of addition and subtraction which are required. Okay. And that was in a context where a step involving addition will take longer and a step not involving addition will take shorter time. So, attempt was to see if there is a chain of 1, if there is a string of ones, instead of doing 1, 2, 3, 4, 5, 6 addition, you perform 1 addition and 1 subtraction. So, there is a speed up there. But of course, in modern hardware, each iteration takes 1 cycle, whether you are doing addition or you are not doing addition. So, it is not considered as a mechanism to speed up things, but it gives us a mechanism to look at positive and negative numbers in a uniform manner and carry out signed multiplication directly. So, now finally, let us look at what is the range of values which a multiplication would produce. Okay. So, when you are talking of unsigned numbers, the result would vary between 0 and this term which is nothing but square of 2 raised to power n minus 1. So, this is the largest unsigned value you have, and square of that is this. Okay. So, this is the largest sum you can get, all right. So, this number could be expressed, I have illustrated with an 8-bit example, n equal to 8. This is what you will have is 2 raised to power 2 n basically corresponds to a 1 here and all zeros. So, from that you subtract 2 into 2 raised to power 2 n, which means 2 raised to power n plus 1, that means you subtract a 1 in this position. So, you get this number and this add 1 which is here. So, this is the largest number as seen in terms of binary you will get. That means, there will be first n minus 1 ones, there will be n zeros and then there is a 1. So, this is a common pattern you will find irrespective of what n is, and obviously, it requires 2 n bit registers to hold the result. On the other hand, when you take sign multiplication, the range would be so the largest most negative number is this and most positive number is. So, if you consider square of this and square of this, this will give you the range, all right. So, this is 2 raised to power 2 n minus 2 within I am sorry, this should not be with negative sign. Okay, the most negative value will come, no, this is not correct, this will be, yeah, this will also be positive actually. So, I should actually ignore, this is the most positive value, and most negative value will come when you multiply most negative with most positive. Okay. So, let us work it out. What you get is minus 2 n minus 2 plus 2 raised to power n minus 1. Okay. So, okay, let us look at each of these first. Most positive value will be 2 raised to power 2 n minus 2. So, which should be this followed by all these zeros. So, that is the largest positive value you get, okay. And the largest negative value you are getting is you have minus 2 n minus 2 is actually this. To that you add 2 n minus 1, which is a 1 here. Okay. So, this is the most negative value and this is the most positive value you get. Roughly speaking, you are not you are getting about half the value. Okay. If you take it approximately, you are getting roughly half the values in magnitude. Okay. But still you have to use 2 n bit registers, you are not utilizing the last bit fully. Okay. So, MIPS has mult and mult u, two instructions are there, mult and mult u. I think in the last lecture I placed it wrongly in the group where overflow is detected and there is no difference in signed and unsigned operation, but actually there is a difference between these two. mult u will interpret the two operands as unsigned integers, right. So, ranges are different, whereas mult will treat them as signed integers and perform multiplication, get results in this range. Okay. So, there is since you are accommodating all the values in 2 n bits, you are providing for 2 n bits, the two registers are H I and L O. Okay. So, in both cases, irrespective of what the result is, it can be contained within 2 n bits, it never goes out. So, there is no problem of overflow. On the other hand, the pseudo instruction which tries to look at only n bits of the result. Okay. There is a pseudo instruction. So, these instruction let me so, let me write this instruction. So, if you have instruction with these two operands, each is n bits, the result is in H I and L O, and you need instructions move from high and you say R 3 or move from low. Sorry, let me put a different register. So, the result which is in 2 register can move to one of the GPRs, the high part, another GPR contains the low part. On the other hand, the pseudo instruction which works with I think multiply with overflow will take 3 registers. So, the programmer is not bothering about the fact that the result first comes to high low and then it is transferred to R 3. Sorry, in this case result R 2 R 3 operand, result is going to R 1. So, we are looking at only n bits of the result and ignoring the higher n bits. So, if the product is bigger than that, if it requires more than n bits, then it is a case of overflow. All right. So, this is the exact description of these instructions. Okay. So, to summarize, we began with our paper pencil method as we understood from early days of school, that you multiply the multiplicand digit by digit. So, same thing translates to multiplying the multiplicand by bits of the multiplier and then adding these partial products with appropriate weightage. So, this we could translate that into a circuit which had one adder for each partial product, and then we sort of wrapped it around, put that in a sequential iterative process where same adder performs addition of various partial products. Okay. Then gradually we made certain observations and tried to improve the circuit. The first improvement was that we reduced the requirement of addition from 2 n bits to n bits and made one of the registers which is holding the multiplicand shorter. Then after having done that, we also noticed that the register requirement can be reduced by sharing a same register between the accumulated sum and the multiplier. Then we moved on to the case of signed multiplication, which was basically derived from a common representation for positive and negative integers. Okay. And the resulting algorithm was Booth's algorithm. Although its original motivation was different, which was to save the time, it is a mechanism which allows signed numbers to be multiplied directly. Okay. And then we have also discussed range of the values and different MIPS instruction which look at the numbers differently and whether they detect overflow or do not detect overflow. Okay, I will stop at that.